Review package. We're just going to seal the deal here. We're starting to get into some identity work. So with this question, we're told, so it tells us that 5 pi over 12 is equivalent to 2 pi over 3, take away pi over 4. That's what we're told. And so if that's true, we want to find the exact value of cosine 5 pi by 12. Now, we know that's not a special angle. Any denominator 12 does not really show up in any of our special triangles. So when we sketch this out, which we can do right now, right? It shows up here in the first quadrant. 5 pi by 12. Of course, this would be 6 pi by 12, right? Or half pi. This would be 12 pi by 12 over here. So 5 pi by 12 would be here. And that's not a special angle. We're not going to use special triangles to find that exact trig ratio directly. So we're going to need to use one of our sum or difference identities. So we'll use our formula sheet here. And we'll say, okay, well, we have a difference identity here. So if we can rewrite cosine of 5 pi by 12 as a cosine of 2 pi by 3, take away pi by 4, because it's equivalent to 5 pi by 12. And then we can use our special identity here, which says that if you have a cosine of an angle take away another angle, you can rewrite it as those individual angles and solve those individually. So we could really say that's equivalent to, using this ratio, where we're going to say alpha represents 2 thirds of pi, and beta represents pi by 4. So it's going to equal to cos alpha cos beta. So cosine 2 pi by 3, cosine pi by 4, plus sine alpha sine beta. Sine 2 pi by 3, sine pi by 4. Okay. And now we just have to be able to solve for these angles. So I'm going to draw them out. So the first angle is 2 thirds of pi. So that's out here. Right? And because that's pi, or 3 pi by 3, 0 half of pi. And that reference angle here is pi by 3. So I can label this special triangle -1 to root 3. And the other angle is pi by 4, which is here, but I don't even need to really draw it in standard position. I could just use my special triangle to add this, because they're all positive out here. 1, 1, root 2 with my pi by 4 special triangle. Okay, so using those two special triangles, I can say, okay, cosine of 2 thirds of pi, cosine is -1/2, so -1/2 times cosine of 1/4, which is 1 over root 2, plus sine of 2 thirds of pi, which is opposite over hypotenuse, root 3 over 2, times the sine of pi by 4, which is 1 over root 2, opposite over hypotenuse. So the last thing we can do is we can write this more simply. So we can write that as -1 over 2 root 2 plus root 3 over 2 root 2. Now most people would write the positive one first. And so I'm going to do that. I'm going to rewrite it. Well, I'll add these together. So root 3 take away 1 over 2 root 2. And then I got to rationalize the denominator. So multiply by root 2, multiply by root 2. And that multiplies by both of those guys. So then I get root 6 take away root 2 over 2 times 2, which is 4. And that's our final answer for that question. Okay. Moving on, we're going to do a word problem. All right, so we're told a question about aiming on a Ferris wheel. It's question 11. Ferris wheel, let's read what we got here. We're told it has a radius of 8 meters. Okay, and Eamon gets on at its lowest point, which is 1 meter above the ground. And we're also told the Ferris wheel makes a full rotation every 100 seconds. So full rotation every 100 seconds. All right, so maybe I'll start by just drawing a sketch of that Ferris wheel out. I know it has a radius of 8. This is 8, right? And I know that it starts at the lowest point 1 meter above the ground. Okay, and so the next thing to do is try to connect that all, so another 8, right, to an axis of some sort. So that value that Eamon's going to get on at is 1 here, right? It's going to go as high as what baseline there is 9. And all the way up here is 9 plus 8, which is 17. So we're told Eamon gets on at the lowest point. So we know that Eamon starts here. And we know, and that's at 0 seconds. This is our time axis. We'll label that time. This is seconds. And this is our height in meters. Okay. And so we know he starts at 1 meter, and after 100 seconds, he's back at 1 meter. So he's got another point there. So we can split this up into halves. So we know that halfway, he's actually going to be at his maximum point, which is right here. Midway, at 25 seconds, he's going to be at the mid-height, and midway between 50 and 100, at 75, he's also going to be there. We can use our knowledge of sinusoidal functions to connect the dots like so. We know that it's going to be a curve like this. All right. So that's question A. Sketch a graph relating Eamon's height as a function of time. And the next thing is to use a sinusoidal function to model Eamon's height as a function of time. All right, so this is A. 11b is we got to turn that into a sine function. So what we do is we typically started with a general sinusoidal function times, we're not even going to choose if it's sine or cosine yet. We'll come back to that. B, I guess we're using time, so t, take away c, plus d. All right. So, okay, first thing is what's easiest. Well, we're going to punch in whatever we think is easiest to find. So we know our amplitude is this guy here, and that's a value of 8. And we also know the baseline is 9. Those are usually the ones to pick off first. So we're going to put in just 8. We're not really going to change anything else for now. Sine slash cosine. B, t take away c, plus 8. Oh, no, pardon me, plus 9. All right. Maybe the next easiest thing to do is to find a period. So, or pardon me, our b value, which is always 2 pi over our period, which is 100. So that means b is pi over 50. So we'll write that in. H of t equals 8 sine cosine pi over 50. T take away c plus 9. Now, the next two things are the phase shift and whether it's a sine or a cosine curve. So but the phase shift depends on whether it's a sine or cosine curve, because we can either choose correct or sneakily one of these values. That will help us make a phase shift of 0, and sometimes that makes less work for us. It doesn't always work. In this case, it does. And when we're done that, we'll have to see what C is. Okay, so we got to remember is that a positive sine curve starts in the middle of its amplitude and rises upward, right? And a negative sine curve starts in the middle of his amplitude going downward at the y-axis. A positive cosine curve starts at its apex, its acme, its peak, and you can think of it decreasing. And a negative cosine curve starts at the bottom of its amplitude and rises. Now, you say, well, which one is this most like? Well, it looks like he's starting at the bottom, right? So it's probably most easy for us to think of it being a negative cosine curve. You could use any of these four correctly to write an equation that will work. But the easiest one is a negative cosine curve because it matches. We're starting at a base, or pardon me, we're starting at a trough. So what we'll do here is we'll say h of t equals 8. And the new thing here is we're going to express what we're choosing, a negative cosine curve. Pi over 50, t, take away c, plus 9. And since we've chosen this negative cosine curve, it would start at its base if it's already here, so we don't think of it shifting to the right or shifting to the left. So therefore, c equals 0. So our last step is to just write out the whole formula. Negative 8 cosine pi by 50 times t. We don't need to say take away c anymore. We can actually just have regular brackets, plus 9. Oh, that's going to make that extra long. There we go. And there's our formula. I'll write another formula or two here. So it could have been, you could have said h of t is equal to 8 cosine pi by 50, bracket t and 50, take away 50. Or you could have said h of t is equal to 8 sine pi by 50, t minus 25. Oops, I forgot. Plus 9, plus 9. Okay, I'm going to use this one. All right, what does question C ask? Question C asks, how high is Eamon after 2 minutes on the Ferris wheel? Okay, so first thing we have to do is we have to say, okay, 2 minutes. Well, that equals 120 seconds. So that means he's going to have gone all the way around and then some. So 125 is out here. That's his next peak. So 120, he's probably somewhere like here, right? So that's probably what we're looking at. So I'm expecting an answer to be somewhere between 1 and 9. I think it's actually kind of looks something like right in the middle. I'm going to say like 5 or 5.5. That's my intuition. So that's going to be our t value. So we're going to say, what's h of 120? That's going to be equal to negative 8 cosine of pi over 50 times 120 plus 9. Now, I'm going to see if I can do this without a calculator. Zeros cancel out. Get negative 8 cosine pi over 5 times 12 plus 9. That's not going to work out nicely, I can see. 12 fifths. Yeah, okay. So we're going to use a calculator. Might as well. Negative 8. I think you actually could use an addition or a subtraction identity to do this, but I'm going to just use a calculator. By 5 times 12 plus 9. I'm in degrees. Radians. Yeah, negative 8 cosine. Pi by 5 times 12 plus 9. 6.5 meters. Cool. Which is not that far off. I was thinking 5.5 meters, just through my tuition alone. So we got 6.5 meters. That's our h of 120. And so, with a word problem, we should usually write out the answer in words. Amen will be 6.5 meters in the air after 120 seconds, or 2 minutes. All right, and last question for part 11, before we get into our proofs. At what time is Eamon 13 meters above the ground? Okay. So this question D, asks when h of t equals 13, what is t? So when is he 13 meters above the ground? Okay. Well, interesting thing is we're not really ever told how long Aim is on the Ferris wheel for. We can take it from the third example, or part C, that he's on it for more than one rotation. So maybe there's probably multiple times that he is at a height of 13 meters. So I'm going to answer the first few. So let's get into this here. So to do this, we use our formula, and we just punch in 13 for our output. So I'm going to put 13 in here is equal to negative 8 times the cosine of pi by 50 t plus 9. The first thing I'll do is I'll take away 9 from both sides. 4 is equal to negative 8 cosine pi over 50 t, and we'll divide by negative 8. We get negative a half is equal to cosine of pi over 50 times t. So it's usually easiest, we say at this stage, to just imagine it's an angle. T is equal to theta. And we'll solve for theta, and then we'll come back to this. Okay, so cosine theta is equal to negative 1/2. Great, okay. So that could be in quadrants 2 and 3. And now adjacent of 1, negative 1, and hypotenuse of 2. That's great. It looks like a special triangle, actually. Well, that's neat. Pi by 3, because that's our root 3, negative root 3. And so that means the possible angles is 2/3 of pi, and another angle is 4/3 of pi. So those are our two possible answers. In here and here, that means our 2 times is going to correspond to those angles. So we know that theta equals 2/3 of pi, which is equal to pi over 50t, and we're just going to solve for pi. Solve for t. So theta 1, theta 2, and it says theta 1, theta 2 is equal to 4 pi over 3, which is equal to pi over 50 times t. So we're going to multiply by 50 on both sides, and 50 times 50. So we get 100 pi over 3 is equal to pi times t. And here we get 200 pi over 3 is equal to pi times t. And then we just divide both sides by pi. Okay, cancel those guys out. And we end up that our time is equal to, he's 1/3 of his way through his trip when he's 13 meters up. And he's also 2/3 of his way through the trip. So So that means these times correspond to 33.3 ... seconds. And this time is equal to 66.6 seconds. So Eamon is at 13 meters elevation at 33.3 seconds and 66.6 seconds. All right. So it's time for our last question. Our last question involves some proofs. We're asked to prove two identities. So, question 12. We'll start with A, tan x cosecant x is equal to tan x sine x plus cosine x. So, as we've talked about before, the first step that's maybe easiest for us is to start by just rewriting anything that's not a sine theta or cosine theta, or sine x and cosine x identity, as or express it in terms of sine and cosine. So the first thing I use is my tan identity to say that it's sine over cosine. And I'm going to use my cosecant identity to call it 1 over sine. And that's equal to, I'll use that same one for tan again, so sine theta, or oops, sine x over cosine x. That should be an x times sine x plus cosine x. All right. So first thing, we've done our first step. So next thing is, well, I don't know, I can multiply these together. So if I can see any way to simplify, I might as well try and do it. So I can write a sine x on the top, and I've got sine x times cos x, and they don't really multiply. So I'm just going to write it like that, sine x cos x. I like to have sine x's in front for some reason. It's just, I'm used to seeing things that way. And on the top here, we've got, this is of course sine x over 1, so they multiply together, and we get sine squared x on the top over cosine x. I'm going to add to that cosine x. Now, that's cosine x over 1. I can't see much to do over here. What I can see is that I can add these together. So I'm going to multiply this one by cosine x and cosine x. Interesting. Okay. Oh, I can see something to do over here. Okay. All right. So that means we get sine squared x over cosine x plus cosine squared x over cosine x. We add these together, and we get sine squared x plus cosine squared x over cosine x. And that hopefully sets off some spidey signals for you, because cosine squared plus, or sine squared plus cosine squared is actually just 1. That's our Pythagorean identity. So we're going to maybe write that right in there as a 1 over cosine x. Okay, so that's as simple as I'm likely going to get on the right-hand side. However, I look on the left-hand side and I say, oh, I actually noticed the sine x's can cancel out. I can divide the top by sine x, and I can divide the bottom by sine x. When I do that, they cancel out. And we end up with 1 over cosine x. And that's it. We're done. QED. All right. Last question, 12b. So b says we've got sine 2x over 1 plus cosine 2x. That's equal to tan x. Okay. So we want to express everything in terms of sine theta and cosine theta. If anything has sine 2 theta, we should turn that into sine theta and cosine theta as well. So we'll turn this top into 2, using this identity here, 2 sine x cosine x is over, I guess we can't change that 1 right now, but cosine 2x, we can choose any of these 3 to represent cosine 2x. So to choose one, I'm going to look over at what I want my right-hand side's denominator to be. If it has a bunch of signs, I'll use one that can turn cosine 2x into something with signs. If it has cosines and sines, I'll use this one. So we'll see. So I can see tan x, so I'm going to actually use my tan ratio here and call it sine x over cos x. Sine x over cos x. Oh, okay. So that means I'm going to want cosine. So I'm going to actually turn my cosine 2x into 2 cosine squared theta, take away 1. 2 cosine squared theta, take away 1. All right. And then we always start on the most complicated side, so the left-hand side definitely looks more complicated. You can see I have a 1 and a negative 1. Those guys cancel out. And so that leaves me with 2 sine x cosine x over 2 cosine squared, x. And I can also see I can divide the top and bottom by 2. So that gives us sine x cosine x over cosine squared x. And this is also looking quite good. I've got a sine on the top and a cosine on the bottom, a sine on the top, a cosine on the bottom. Now, I want you to remember that this really means sine x cosine x over, to be squared means to be multiplied by yourself. So it's the same thing as saying cos x times cosine x. And so I can divide the top and bottom by cosine x. And that cancels this guy and that guy. So that leaves us with sine x over cosine x equal to sine x over cosine x. And that is that. We're done, guys. All right. Stop in during flex block if you have any questions about this stuff. Other than that, good luck studying.